cylindrical coordinate system have z-axis and origin of coordinate system, and we can choose some rigid line, fixed line into space. And let's consider that there is a plane which is perpendicular to z-axis. So if we want to define a position of a particle in this coordinate system, so we make a projection of this point to this plane, and we connect origin and this projection, and this is coordinate rho, and this angle is coordinate phi. So we define position by three coordinates: rho, phi and z. This system has base vectors. So the base vector of z-axis is k, base vector of rho axis follows the rho direction and it is I rho, and there is another one, coordinate vector of coordinate axis, so it is I phi. This last vector is perpendicular to both and doesn't follow this line. Okay, it's a different line. So we can write base vectors. It is I rho, I phi and k. So if you want to draw a velocity vectors, we need to make parallel lines with coordinates. Okay, so velocity, and velocity is a vector defined by components. It means components in these three axes. So we will have v rho, v phi and vz, and we can rewrite it like this. So it is v rho I rho plus v phi I phi plus vz kz, and these components are defined like this. So rho is rho with dot, it's a derivative of rho with respect to time. V phi is rho phi dot, where phi dot is derivative of phi with respect to time, and vz is z with dot. So we have three components of velocity. So in positive directions we have v phi, v rho and vz. What about acceleration? Acceleration has also components in these directions, rho, phi and z. So it is a rho plus a phi plus az. So we can formally rewrite it to a rho by I rho plus a phi by I phi plus az k. And these components are defined like this. So it is rho with two dots minus rho phi dot square. A phi is rho phi with two dots plus 2 rho phi with dots, and az is z with dots, two dots, where rho with two dots is a second derivative of rho with respect to time, and rho phi with two dots is second derivative of phi with respect to time. And naturally, z with two dots is second derivative of z with respect to time. What if some force acts on this particle? So this force must be defined also by components. So it has F components, rho components, phi component, and Z component. So it can be rewritten like this. It is F rho by I rho plus F phi by I phi plus Fz by K. Okay, so I can draw F components. Like this. And I can also draw components of acceleration. It's in the same direction, so it is a phi, this is a z, and this is a rho. What about inertia force, so called D'Alembert force? So similarly, we can define D'Alembert force by its components. So it is given by d rho, d phi, and dz. What can be rewritten into this form? It is d rho, I rho, plus d phi, I phi, plus dzk. And as we know, the orientation of D is given by negative orientation by positive acceleration. So it's against acceleration, so this is component d phi, this is component dz, and this is component d rho. And generally we can write a general equation of equilibrium. So it's given by this formula. So sum of all forces plus D is equal to 0. And because we are in three-dimensional system, we can make three equations in scalar form from this one vector equation. So in rho, phi, and z direction. So there will be that it is sum of all rho components of all forces minus d rho is equal to 0. Sum of all phi components minus d phi is equal to 0, and sum of z components minus dz is equal to 0. So, like this. Following this definition, we can write that d rho is m by a rho, d phi is m by a phi, and dz is m by az.